Hello friends, so now we are going to discuss the second method of speed control, that is called armature resistance control method. Let us see the mathematics part of it. This is the basic equation from which we can derive all the methods. We can see that over here that if we do not change voltage or if we do not change flux, then the second term is the one which can affect the speed. Now, what you can do is that you can insert some resistance in series with the armature, because existing armature's resistance you cannot change, but you can always insert anything in series. And you know the property of a series connection, that when you add a resistance in series, the overall or total resistance increases. So as this is the case, now you can see that the second part, which is slope of these characteristics or the voltage drop, you can say, is increasing, because of which now the speed is going to go down, right? So armature resistance control method can be implemented by inserting an external resistance in series with the armature circuit. When you do that, see, green one is the characteristics which is original with no external resistance. Now, if I increase I add some resistance with Rex1 value, the characteristics goes down. But you can see that the no load part, which is nothing but the intercept part, V divided by KB5, is constant. So here the characteristics just the slope only increases and the no load speed remains same. As I go on increasing the external resistance Rex1 to Rex2, Rex2 to Rex3, the slope of the curve goes on reducing. Now you can see the black line with the load torque is equal to constant shows that initially with no external resistance, the motor was operating with this load at speed omega 1. And now with the Rex3, it is operating at omega 2. And there is a large difference in the speed omega 1 and omega 2. So this is the method which is giving you wide variation in speed, right? So if I use this method for constant load torque, I'm going to get a very huge variation. So this method is not good if I want to have a say constant load where I want that the speed regulation should be good, because here the speed regulation is poor. So for one value of external resistance, if my load varies, then the variation in speed is too much, right? So this is the disadvantage of this method. Also, this method is a lossy method where you are inserting resistance, so I square R loss increases. Resistance, external resistance is also a costly affair. So this is a costly and a lossy method. So in practice, in paper it is all right, theoretically it is all right, but these days there are more advanced and better methods are available. So this is the method which we do not use much in practice, right? So this is once again the slope of the line decreases, as we have already seen. No load speed remains same. Speed regulation is poor, as we already talked about, and as this is an inefficient method, not used much in practice. So this is the armature resistance method, which is for the DC shunt motor or separately excited motor. It can be done for both these motors. There is no issue in it, right? The characteristics remains same. Now, if I use series motor and if I apply the same method, that is I insert resistance in series with the armature, the armature resistance, in fact, over here I have assumed that this RA is a combined resistance of field and armature, right? Because armature and field are in series in case of series motor, right? So if I insert a significant resistance Rex in series, I can have a variation in speed control. So this is something like this. So here you can see that the characteristics with external resistance in series with the armature is below the original characteristics, and as the load increases, the gap or the drop in speed also increases, right? So you get a poor speed regulation. So new curve is below the old curve, speed decreases, and more drop in speed at higher loads, right? Of course, it's a series motor, so it is not going to cross and go into second quadrant, right? Of course, here also this is the inefficient method and so rarely used, right? That is all about the armature resistance control method. Now the field control method. So here once again look at the speed equation. So if I change the excitation, that is flux, you can see both the part V divided by KB5 part also changes, and IRA divided by KB5 part also changes. So what do I do? If we reduce the flux, the V divided by KB5, which is a no load speed, that increases, and minus IRA divided by KB5, which is the slope of this curve, that also increases. Now, why I have always decreased flux? Because flux cannot be increased. The machine is designed, the core part, magnetic parts are designed to withstand certain flux density. If I increase the flux, it crosses that limit and it will go into saturation. So that is something which you cannot allow. All the machines are already operating near the knee point of the magnetizing curve. So flux increase is not an option. So flux can be reduced only. When you reduce the flux, speed increases. So this is the method which gives you speed above rated speed, right? Speed above rated speed. And both no load speed also increases and the slope of the characteristics also increases. Let us see in the graph part. You can see over here the bottom one, the lowermost curve is with IF rated, that is excitation current rated. Then I have reduced the field excitation to IF1. So IF1 is less than IF, and then IF2 is less than IF. So if I reduce the flux, you can see the characteristics is above the rated characteristics, and the line original curve was almost parallel to x-axis or torque axis, but here the slope of the line increases. So this is the feature which you are supposed to observe for the field control method. So here flux cannot be increased beyond rated as it causes saturation. We have seen that it can be reduced only. Speed decreases, sorry, increases above rated speed, and both no load speed and slope of this characteristics increase. Now, what is the limit? Generally, this is called a field weakening region. So we'll see in detail in the advanced sessions that field weakening is also having limits. Generally, it depends on the mechanical safe limit of the speed. And whenever this method is used, in most of the cases, twice the rated speed is the limit, right? But that is something which we are going to see in the later part of the this particular subject. Here we are introducing the concept of how different speed control is achieved, right? So this is all about the different speed control methods, that is armature voltage control method, armature resistance control, and field control. Now this field control is difficult to achieve for DC series motor as things are in series. So flux, how to reduce flux? Because whatever is armature current, same is going through the field winding. So it is difficult to reduce the flux. Yeah, there is a method known as field diverter by which in that particular thing you connect a low resistance in parallel with the field winding. So you divert some of the field current, and that is how you can use, but not that very popular. So field control is not that easy for DC series motor. So that is something which we are not going to discuss right now, right? So these are all the methods. Now in subsequent sections, we are going to discuss how these are implemented, how to achieve armature voltage control method, what are different ways, the comparison of different methods, and so on and so forth is what we are planning to discuss in our subsequent lectures, right? So that's all in this particular section. We'll continue with the same in our next